Good morning. So today we'll talk about quantum gates. So far, we've talked about what the allowable states of a quantum system are and what happens when we measure the state of a quantum system. So these are encapsulated in the first two axioms of quantum mechanics. Quantum gates address the issue of how the state of a quantum system evolves in time. And this is encapsulated in the third axiom of quantum mechanics. Okay, so I'll start by reviewing all these axioms. One thing some of you might find surprising is just how simple these axioms are, given that they tell us about, they are the axioms of quantum mechanics. So, well, the interesting thing here is, well, the axioms are very simple, but then, on the other hand, all the possibilities that they create and all the quantum behavior that they create, that they allow for, is actually very complex and interesting. Okay, so first the superposition principle. What does it tell us? It tells us that if you have a k-level system, like the k energy levels of an electron, then the state of the system is a point on a k-dimensional ball in a k-dimensional complex space. So here, more precisely, what it says is that there's a k-dimensional complex vector space with a preferred or standard basis, which consists of these k states, which we label 0 through k minus 1, and they represent the k energy levels of the electron. Now, this is, of course, a complex vector space. It also has a geometry. So, it has this notion of orthogonality between these states, and there's an angle between other states, which is defined by an inner product. And so this complex vector space with inner product is called a Hilbert space. Okay, that's just terminology. And now the state of our quantum system is a unit vector in this space, psi. And it's a superposition of these basis states with complex amplitudes, alpha naught through alpha k minus 1. Okay, all this we've seen before. Now, what happens when we measure the system? So in general, a measurement of the system involves choosing an orthonormal basis. So we choose an orthonormal basis. Let's call it U0, U1, UK minus 1. So this is our choice of orthonormal basis. And now, this is the state vector. Okay, so now suppose we want to know what's the chance that the result of the measurement is j. Okay, so for example, j equal to 1. Well, the answer is it's the square of the magnitude of the inner product between u sub j and psi. Okay, this is also what we called, in a simpler setting, cosine squared theta, where theta is the angle between psi and u sub j. Okay, so let me just say this a little more formally. So let's call this, so let's say psi was alpha naught 0 plus dot 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 alpha k minus 1 k minus 1. And suppose u sub j was beta naught 0 plus dot 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 beta k minus 1 k minus 1. Then the inner product between u sub j and psi is just beta naught complex conjugate times alpha naught plus dot 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 beta k minus 1 complex conjugate alpha k minus 1. There are different conventions about whether you take complex conjugate of the amplitudes of the first vector or the second one. We'll use the physics convention, which says to take the first one. This is also, if you write a row vector corresponding whose coordinates are beta naught complex conjugate through beta k minus 1 complex conjugate, and the column vector corresponding to the alphas. Okay, so now there's we talked about, this is of course the standard vector notation. Here we are looking at ket notation. So there's a very nice notation for inner products, which was also introduced by Dirac. It's a completion of this ket notation. So you can write this row vector also as what's called, so this notation, the complete notation is called the Bra-Ket notation, and this vector is denoted by u sub j with this bracket pointing left, and this is called the bra, and that is called the ket. So bra u sub j is exactly this vector in the dual space. It's the conjugate transpose of the original vector. And so now if you want to write out the inner product, you just write the inner product is equal to bra u sub j and then ket psi. So the probability you see j is just the square of the magnitude of u sub j squared. And of course, if the outcome of the measurement is j, then the new state psi prime is just u sub j. Okay, now finally we get to the third axiom of quantum mechanics, which talks about how the state of the system evolves in time. So the state of our system is this point on the unit ball in this k-dimensional complex vector space. And now the axiom is really elegant. What it says is that the evolution of the system is via a rotation of the Hilbert space, of this vector space. So here's what it's saying. What we do is we take this complex vector space and we give it a spin. So we rotate it in some direction. Now, everything inside this vector space rotates as a result. So also the state of the system. So it rotates from where it was to a new state. Okay, so this is psi nu, the state after the evolution of the system. Okay, so now let's try to understand what this is telling us by looking at, well, let's look at the picture in 2 dimensions where this notion of rotation is much easier to picture. So let's say that we are working in a 2-dimensional space, and our state happens to have real coefficients, so we can actually draw the picture in on the 2-dimensional plane. This is our standard basis, the 0 and the 1 state, the ground and excited state. That's our superposition. Okay, so what happens is, to evolve the system, we give a rotation to this space, and so if we rotate it through some angle, the new state 0 moves to this new position, which I've denoted u of 0 for reasons that will become clear in a minute. 1 rotates correspondingly, and of course psi rotates the way it does. Now, one thing you'll notice here is this is a rigid body rotation, so angles between vectors are preserved. So for example, if this angle were theta, well, that's the same as this angle theta. Or if you had another state in here, phi, and that made an angle of theta prime with psi, then after the rotation, this is where it would sit. So that would be, well, by this same notation, which, this is the new place it ends up at, and that angle is bound to be theta prime. Okay, so let's try to understand this a little more formally. So here's formally the rotation of a space is given by a linear transformation, which we can represent as a matrix. So let's do an example in 2 dimensions. So let's say that we have our state vector in this 2-dimensional space with real coefficients. And now we rotate it through an angle. We perform a rotation of the space through an angle theta. So what this means is we are rotating 0 to this, the state 0 to this new state, which makes an angle theta. But of course, everything else moves by, the entire picture is getting rotated through an angle of theta. Okay, so what happens to, how do we represent these new states? So under this transformation, the state 0 moves to this new state, which has coordinates cosine theta and sine theta. So it moves to cosine theta 0 plus sine theta 1. And the state 1 goes to, this angle is theta, so it's cosine theta 1, and it's minus sine theta 0. Okay, so the way we represent this is via this. So this rotation can be described by this linear transformation r theta, whose columns are exactly these vectors: cosine theta sine theta minus sine theta cosine theta. Right? Because when we ask where does the state 0, which is in our standard vector notation 1, 0, if you want to know where did this get mapped to, well, this picks out the first column of this matrix, cosine theta sine theta, which is exactly what we had there. And if we had 0, 1, then that would pick out this second column of the matrix. Okay, now there's also a different transformation we could do, which is a rotation through minus theta. And if you work it out, what a rotation through minus theta is represented by, it's a very good exercise and you should do this, is this matrix where this minus sine theta and sine theta switch places. So this is exactly r of theta transpose. And now, of course, these satisfy the relation that r of theta times r of minus theta is the same thing as r of minus theta times r of theta, which is the identity. If you rotate through theta and then you rotate through minus theta, you come back to where you were. But you can also write this as r of theta times r of theta transpose is the identity, which is also r of theta transpose times r of theta. Okay, so we will see that not only in 2 dimensions and not only for such real rotations, but this is going to be the property of linear transformations that represent rotations of a vector space. And such matrices are called unitary. These are called unitary transformations. And so in the next video, we'll study these more formally and their properties, etc.